IMO problem. Find all triples of positive integers a, b, p with p prime and p's power of a equal to factorials of b plus p. For the method, we can test a few numbers and try to find something. Obviously, the first prime is 2, so we let p is equal to 2, and then we get a2 equal to b's factorial of b plus 2. Obviously, we can immediately to get a is equal to 2, b is equal to 2, and this is a solution. But we are not sure if this is the only solution when p is equal to 2. Okay, so we need a reasoning. A squared equal to plus 2 greater than 2. So a squared greater than 2. A greater and equal than 2. Therefore, b's factorial plus 2 is equal to a squared greater and equal than 4. So b's factorial greater and equal than 2. b greater than equal 2. Now that b greater than 2, so the right side is an even number. That means a must be even. We can set a is equal to 2k. K is an integer. Then we have 4k squared equal to b factorial plus 2 divided by 2, and 2k squared equal to b's factorial divided by 2 plus 1. That means b cannot greater than 4. If b greater or equal than 4, b's factorial divided by 2 will be an even number, and the equation will not be right. This means b must less and equal than 3, because if b greater than 4, b's factorial divided by 2 will be an even number, and even number plus 1 will be an odd number, so contradiction. Because b greater than 2, so the only number is 2 or 3. If b is equal to 2, we get a is equal to 2. So if b is equal to 3, we get a squared equal to 3 factorial plus 2. It's equal to 8. So there's no solution in that case. One more sample. If p is 3, we have a3 equal to b's factorial plus 3. 3 is a prime. Then we have a3 equal to b's factorial plus 3 greater than 3. So a3 greater than 3. So a must greater than 1. Greater than equal to 2. And then we have b's factorial plus 3 is equal to a3 greater and equal than 2, 3, 8. That means b's factorial greater and equal to 5. 8 minus 3. So b must be greater than 2. And so b can greater and equal than 3. Because 3's factorial is 6. So b greater than 3, and this is 3. So that means 3 is a factor of a, we can set a is 3k. K is an integer. Same way, we have 3k, 3 equal to b's factor plus 3, divided by 3 in both sides, and we have b's factor divided by 3 plus 1. Let us watch this equation closely. If b is too big, say it is greater and equal than 2p, which is 6, then b's factor divided by 3 will still be times of 3, say 3m. And then the left side and the right side will contradiction, because the left side 3 2k3 equal to 0 mod 3, but the right side it will be 1 mod 3. So contradiction. That means b must less than 2p, which is 6. Because b greater than 3, so b can only be 3, 4, 5. And we can check which one has solution. So only 3 cases we can check one by one. If b is equal to 3, and a3 equal to b factor plus 3, and equal to 3 factor plus 3 is equal to 9. So no solution in that case. If b is equal to 4, then a3 equal to 4 factor plus 3 equal to plus 3, 24 plus 3 equal to 27. So in this case, it has a solution. So we get the second solution. If b is equal to 5, we have a3 equal to 5 factor plus 3 equal to 5 times 4, 3, 2, 1. And this is 26 plus 3. So it is 123. So no solution. Now we have two samples. We can get some hint now. We see b is always greater than p, but less than 2p. So we think b possibly less than 2p, but greater and equal than 1p. And from that result, a is equal to 3. A is equal to 3. So when we say 3k, seems k is always equal to 1. And a always divided by p, because a is divided by 2 here, and here a divided by 3. So possibly a may be equal to p. So this is the hint we get. Next step, we will use the same method to go with the solution. Now we go with the solution. We will prove it is impossible for b less than p. Suppose b less than p, then we will have 3 cases. Suppose this is p over here. And if a is here and b is here, see b less than p, but also less than a. So this is the case 1. But a can be over here. In this case, A less than P greater than B. And A can be here. In this case, A less than B and less than P. We will prove all of the three cases are impossible. For case 1 and case 2, we can put them together. In both cases, B is less than A. So A is greater than and equal to B plus 1. So A to the p's power greater and equal to B plus 1 to the p's power. And then we break it up. And we get it will greater than B to the p's power plus P. Because P greater than B. P greater than B. So B to the p's power greater than B to the b's power. So, but B to the b's power greater than B's factorial. So it will greater than B's factorial plus P. So B's factorial plus P is impossible to equal to A to the p's power. So this is impossible. So case 1 and case 2 has no solution. Case 3, A less than B less than P. See here, A less than B. So A divided B factorial. It also means A divided P. But A greater than 2 over here. So A cannot be 1. And A divided P, so A is equal to P, because P is prime. But we know A less than P, so it is possible to have A equal to P. So contradiction. Overall, case 1, 2, 3 are all impossible. That means B must greater and equal than P. In this case, because B greater than P, so B factorial plus P can be divided by P. And B factorial plus P is equal to A to P's power. So P can divide A to P's power. And then P can divide A. So we let A is equal to Kp. Here K is an integer. Then we have A to P's power is equal to K to P's power, P to P's power, and equal to B factorial plus P. We divide by P in both sides. We have this equation. And obviously, if B greater than 2P, that means after it divided by P, we still have another P can be divided. So the left side, if we divide by P, the remainder will be 0. Means Kp, Pp minus 1 equal to 0 mod P. But the right side, if we divide it by P again, the remainder will be 1. So mod P is equal to 1. So this is the contradiction. Now we get the conclusion. B must less than 2P and greater or equal than 1P. The next step, we will prove K must be 1. K can only be 1. That means A is equal to P. If K not equal to 1, we have two cases. K less than or equal to B, K greater than B. In the first case, K less than or equal to B means K can divide B factorial. And P is a prime. And P less than B, so K divide B factorial divided by P. So this part. That means the right side divided by K, the remainder will be 1. So equal to 1 mod K. And the left side divided by K, the remainder will be 0. So equal to 0 mod K. So this is the contradiction for case 1. For case 2, suppose k greater than b, then we can have k greater than or equal to b plus 1. We will prove k to p's power multiplied by p to p's power equal to b factorial plus p is also impossible. Because b less than 2p, therefore b less than or equal to 2p minus 1. That means b factorial plus p less than or equal to 2p minus 1 factorial plus p. Based on the famous inequality, if xy greater than 0, then we have xy less or equal to x plus y divided by 2 square. If we let x equal to I, y is equal to 2p minus I, and we have xy less than or equal to p squared. Now we see 2p minus 1 factorial, and we resequence them. The first one and the last one, put them together. The second one and the second last, put them together. The sum will always be 2p, and totally we have p minus 1 pairs, because in the middle there is a p. So totally it is less than or equal to p to 2p minus 1. So we have proved the right side is less than or equal to p to 2p minus 1 plus p. And we see the left side. The left side obviously greater or equal than b plus 1 to p squared, p to p squared. And b greater than p, so it greater than and equal to p plus 1 to p's power, p to p's power. And the first one, we can break it up. Obviously, it greater than p to p's power plus 1, and multiplied by p to p's power. And that's greater than p to 2p minus 1's power plus p. And obviously, this is greater than or equal to b factorial plus p. So that means for this equation, it is more possible, because the left side will greater than the right side. So it is impossible. Now we get the conclusion. K must be equal to 1. It cannot be any other number. The problem is simplified to p to p's power is equal to b factorial plus p, and b less than 2p but greater than or equal to 1p. So the problem is simplified. Because we already got the result when p is equal to 2 and 3, now we assume p greater than and equal to 5, which is the next prime number. And we will show b cannot be p. B must greater than p. Say if b is equal to p, and this equation become p to p's power is equal to p factorial plus p, and it is equal to 1, 2, 3 p plus p, and it less than 6 p to p minus 3's power plus p, because each item is less than 2p. And in that sense, the p to p's power, because p greater than 5, so p to p's power greater than 125 p to p minus 3's power. And this one is obviously greater than 6 p to p minus 3's power plus p. So the left side greater than the right side, obviously. The equation cannot be approved. Means b cannot be equal to p. Now, if b greater than p, we suppose b greater than or equal to p plus 1. As we know, p is a prime and also an odd number. So p plus 1 divided by 2 is still a number less than b factorial. So 2 multiplied by p plus 1 divided by 2 multiplied by p plus 1 can still divide b factorial. Means p plus 1 square divide b factorial. However, does p plus 1 square divide p to p's power minus p? Because p is a prime, so it is an odd number. We let p is equal to 2n plus 1. N is an integer. Then from here, p to p's power minus p equal to p multiplied by p to 2n's power minus 1. And here, we can use the factorization method. Say that q is equal to p squared. And then p to 2n's power minus 1 become q to n's power minus 1. And factorization become q minus 1. 1 plus q 3 plus dot 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 plus q to n minus 1's power. And we replace q with by p squared. We get this factorization. And p squared minus 1 can become p minus 1 multiplied by p plus 1. And for that side, because p is equal to p plus 1 minus 1, so when we divide it by p plus 1, the remainder will be minus 1, mod p plus 1. So p squared, or p to 2i's power, will be equal to 1. The remainder will be 1 divided by p plus 1. That means each of them, the remainder is 1. So totally, the remainder will be n. And n is p minus 1 divided by 2. So when we divide this section by p plus 1, the remainder is p minus 1 divided by 2. It is not a 0. So that means that side, p to p's power minus p, is not divisible by p plus 1 squared. That means this is not approved. So p greater than equal to 5 is not approved. So p can only less than 5. And the only number is p is equal to and 3. So we get all the solution. All the solution is when p is equal to, and another one is p is equal to 3. So only 2 solutions. For this problem, we see a to p's power. We may think about Primitus-Leitao theorem. Maybe someone can think about that method. Maybe we get out another solution. Means use Primitus-Leitao theorem.